Okay. Definitely it will give a slight effect in terms of the voltage and the current that flows depending on the circuits. Okay, example of sine wave for AC. So again, the differences you can see clearly. Okay, power you can see is either one direction. One direction over here for DC, and for alternating current for AC. Okay, let's come back to our thesis.
So what is your basic work on these kind of electrical circuits analysis?
Basic working circuit.
I mean, your title is simulating the authenticity of power divider rule for electrical AC circuits. That means you are trying to prove the power divider rule is working on electrical AC circuits.
Yes, exactly. But before that, that's what I did. I tried to explain the difference between how the DC circuit and the AC circuit differs. So later, we will be concentrating more on AC circuits. So as it is, introduction to the project. Okay. So when you before we touch on the power divider and the what you call the journal, ISI journal, and then the new formulation. Okay. There are some conventional methods being used previously, which is called as current divider rule and voltage divider rule. So most of the these concepts, we call it conventional. So those days, most of the researchers and so on, they were emphasizing more on this conventional methods. Okay. So what we are going to do over here in this project, or what we have done is simulate project or analyzing the power divider rule. Now, basically, it's also a mathematical formula. Okay. By using the power divider rule, and this power divider rule will be confirmed further by using the simulated software. Okay, and definitely if you look at it here, over here, new formulation considered from ISI Journal Electronics were UK. So based on the previous researcher, okay, the research has been done on DC circuits. So over here we are going to concentrate on AC circuits.
Okay, got it.
Okay. So where total dissipated power equals to total supplied power. So we need to say whatever power that is being supplied over the configuration, the total comes back to the power. The total power of the configuration.
Okay, go ahead.
The objective of the research to understand the mathematical formula works in relevant. This one I explained better. Works in relevant to AC circuits. Now, analyzing the authenticity of PDR on electrical circuits using circuit maker software. So the main objective of the research will be, we are going to use the mathematical formula, okay, whether it works relevant to the AC circuits, and at the same time we are going to analyze the authenticity of PDR on AC circuits, whether it really works on AC circuits. Previously it's proven, okay, by the earlier researcher that it worked on DC circuits.
Okay.
Mr. Desmond, I'm just curious. I'm not from your field, by the way. You're using a certain software, right? What circuit maker software?
Circuit maker software.
So what makes you choose this software?
Okay.
There might be other softwares, right?
Basically, when you look at it, this is a high-end software. Okay, where some even difficult configurations can be designed using this software, and also another most important area is user-friendly.
So previously, the research done on the DC circuit was also using the software?
For AC circuits.
For DC?
Yeah, it can be checked using the same software.
Yeah, normally circuits you can simulate in any software, but the circuit maker is okay. Still, it's a free version, student version. Still, you can simulate it. So you can. It depends on the circuit. It all depends on the software. Any software you can, you also can simulate in MATLAB. MATLAB also you can
MATLAB.
simulate, yeah.
Those days I used to
And
use the MATLAB.
why is this rule, power divider rule is, why is it better than the current divider rule and voltage divider rule?
Current divider rule basically you will be using to check on the current values, whereas voltage will be you will be specifically focusing on voltage.
So now you want to specifically focus
Power.
on power.
That's why the basic explanation was I touched on the power.
So the new formulation you taken from one ISI journal.
ISI journal.
So is it referred in your?
Yes, definitely.
Yeah, so it is now. Okay, go to the next one.
Scope and limitation of the research.
Yeah, page 15.
So over here, okay, the scope and limitation will be based on ideal simulation for DC circuits, ideal simulation for AC circuits, and a non-ideal simulation for Monte Carlo for AC circuits. Okay. Now the difference over here for ideal simulation will be using most of it. Will be focused on fixed values. Okay, where external factors are non-influenced. So that is why it's called ideal simulation. So later there will be some waves on the graphs and the proven over there. So based on this, okay. Ideal simulation for AC circuits. Basically now we are. That's why just now, doctor, you asked whether we are doing the simulations right. So later we can see simulations are done for AC circuits and DC and AC circuits.
So you have done 3. The first one is ideal simulation for DC. Second one is ideal simulation for AC. Third one is non-ideal simulation.
Yeah, which is called Monte Carlo. Very interesting name. Yeah, that actually will make us easier to remember. What is why Monte Carlo is a bit different name.
Yeah, Monte Carlo you also can find in ORCAD.
Yeah.
There is another electronic software, they got Monte Carlo.
Monte Carlo. So under Monte Carlo, using a random sequence of values. That's where the values will change or vary. Okay. External factors influence even in terms of malfunctions of the components of the nodes as well.
Okay. Go on.
So hypothesis of the research. To what extent the PDR works in AC circuits? Well, and its authenticity, including resonance due to magnified current and specific frequency. So when you say resonance due to magnified current, okay, this is due to some of the components of the circuits. Okay, so there is we can even in another way we can even see kinetic energy is what we call a charge or something else. Okay, that will create resonance. Okay, so probably later in the graph we can see that as well. Okay, so we are going to see to what extent PDR works in AC circuits. Okay, because this is our focus now. PDR on AC circuits. Okay, next organization of thesis overall. Now, as I mentioned earlier, consists of introduction, literature review. Definitely, we will touch on this as well. Analytical concept, results and discussion, conclusions and recommendations, reference and appendix. Okay. So under literature review, okay, roughly about 200 journals have been referred. Conference, book, manual, lecture notes are referred in total, but only 100 citations are included in thesis. 100 citations which are relevant to our work on this. Okay, you can see the thesis over there. Okay, under literature review, basically these are the some of the research done on what we call same field. Okay, which I just mentioned the name. Antenna design, isolation characteristics of resistors. Okay, hybrid power dividers. Under the what you call the thesis over there, documentation is clearly explained how this formula worked, who published it and so on. Okay. So frequency dependent impedances, transmission lines, transformers. Okay. So Wilkinson power divider, this is one of the famous, we can see over there in the thesis, which concentrates on high frequency systems, waveguide impedances matching, Wilkinson power divider lump elements, dual band branch line coupler, dual frequencies matching, radio power divider, millimeter wave frequencies, power sharing in multi-layers. Okay, this is another interesting area, power sharing in multi-layers, transmission of Kersey-Gaussian wave flows, phase shifter, and improved power divider. And another one next is UHV band performance, even mode analysis of power divider, fit algorithm in power computation, balloon, filters, oscillators, UWB antenna array, power meter calibration, utilization in unlicensed frequency band, and four-way divider. So these are the what you call the areas that have been researched previously. Okay, so it's very well defined in the thesis.
Yeah, I saw you have written in the literature review part. Go ahead.
Okay. Electrical circuit making software. Okay, this is the one earlier, doctor, you asked what you call the software that we'll be using. It's known as Circuit Maker 2000. It's the most powerful, easy to use schematic capture and simulation tool to draw, edit, test, and simulate electronic circuits. It's a high-end design software. Basically, very complicated schematics. You can even use this software to draw, and it's not so expensive. Okay, that's the most interesting part, because nowadays you want to get any softwares. Another factor that we need to concentrate is the cost.
There is one more factor you have to remember. Some companies like Intel, they don't tell what kind of software they are using.
Yeah.
So nobody knows what kind of system they are using to design their chips.
In India.
Because they patent it. So therefore they don't tell you what kind of. So outsider, even the academic institution, they have very very short of information about their technologies. That's how it works.
Certainly, it's kept confidential.
Yeah, they don't share it academic. So industry is different, academics is different.
Maybe it will be due to the competitors as well. Okay, software setups. The software was tuned to run DC and AC simulations as well as the Monte Carlo analysis. Okay. So we will be emphasizing on all this using the software, DC, AC, and Monte Carlo analysis. Okay, electrical circuits configuration. So this is where we are coming into the analytical part, electrical circuits. So since earlier I already explained in deep, okay, or in with the basics. So basically over here we know, based on the diagram we can figure out what is this circuit for. Okay, this is a series circuit. You can see how it's being arranged. Okay, R1 resistor 1 with a 1 kilo ohm, and R2 1 kilo ohm. Okay, so it's being arranged with a 10 volt of voltage only. Okay, power supply. Parallel circuit. Okay, this is a ground. 10 volt. Again, when you look at it, resistor 1, resistor 2, they are arranged in parallel. So basically, this will be the basic on how the rest of the DC AC circuits will be analyzed using PDR. So electrical circuits parametric setups. So input source over here will be using an input source of input voltage of plus minus 10, okay, for AC. Input frequency of 50 Hertz. So earlier I already mentioned for AC will be usually 50 to 60. So we are taking 50 Hertz over here. And the components, the values for resistor varies 10 to 10 mega ohm. Okay, the range. The values for inductor varies 10 to 10 micro Henry. The values for capacitor varies 10 to 100 nanofarad. Okay, so the values will be within this.
So you are studying the power divider rule using the stimulation using different values of that component.
Yeah, definitely. And this is another one will be Monte Carlo
So the input source is fixed.
for within the range. Within the range. Okay, under results and discussion, conventional rules.
Yeah, just now you already discussed all those things. Go ahead.
Ohm's law, and I mean, since we already gone through earlier, so it will be easier for us to understand what is Ohm's law. And what we call power law, voltage divider and current divider rules. Okay, so basically under conventional rules, these are the main rules. Okay, so newly published rule will be power divider rule. Okay, as we are going to emphasize on that. Now sources over here will be AC and DC supplies. Okay, components, as I said earlier, based on the earlier explanation, these are the main three components that we'll be emphasizing: resistor, inductor, and capacitor. Analysis of PDR in circuit making software. So these are the combination. If you look at it in series configuration, RL, resistor, inductor, and resistor, capacitor. And then in parallel, resistor, inductor, and resistor, capacitor. And another with the three combinations over here: resistor, inductor, capacitor, series and parallel for both, and the simulation system, AC simulations. So Ohm's law.
Yeah, this part we already covered. So go to next.
Next slide.
Next slide.
Conventional voltage divider rule. Okay. So over here the total voltage. Basically under conventional voltage divider rule, we are going to focus on the voltage. Okay. So how we are going to calculate? So we are going to find the voltage. First of all, we are going to find the voltage across R1, resistor 1, and also the voltage V2 across resistor R2. So the formula will be V1 equals to R1 divided by R1 plus R2 times with the total voltage supply. Okay, and the second, to find the voltage across R2, again the same formula, V2 equals to R2 divided by R1 plus R2 times with the total power supply. So you will get V1 and V2 over here. So when you when you take V1 and V2, you can total up to the total voltage supply. Okay, next is the conventional current divider rule. Now earlier we focused on voltage, now we are focusing on current. So we are going to calculate how to calculate the current across R1 and also the current across R2. Okay, so current across R1 will be R2 divided by R1 plus R2 times with the total current. Okay, and for current across R2, the formula will be the same, R1 divided by R1 plus R2 times with total current supply. So when you add up these two, you get the total current supply. So this is one of the conventional current divider. Okay. Okay. This newly published power divider rule. Okay. The total dissipated power is equal to total supply power regardless of circuit configuration, whether it is serial or parallel. Okay. According to this researcher, okay, the total dissipated power is equal to the total supplied power regardless of circuit configuration. Whether it's
I have a question. You said the newly published rule. This paper was published in 2006.
6.
So since 2006 until now, was
No.
there any other rule?
No. This research has been done on DC circuits.
So this is the only published power divider rule,
Yeah.
which is cannot be questioned, patented and everything.
So far, I don't think so.
Normally theories they don't do patents.
Yeah, but this was published in 2006.
Six,
Theory might change, right?
Yeah, but
From 2006 until now, from your literature work, no changes
No changes
on this theory.
so far. No. But then here we are concentrating on AC. So meaning to say that these are okay. When you look at it over here, see generally the electrical engineering studies have current and voltage divider formula for that circuit analysis, and also some general formula for power. Okay, let's go through this first. Okay, there is no specific formula for power such as current divider, voltage divider rule. This thought helped me to come up with a power divider rule. So basically that's how the previous researcher came up with power divider rule for DC circuits. According to
Yeah, I got
it
it,
was
I got it.
published in 2006.
Thereafter you didn't see any other improvement on this?
So basically the next area that after this I'm doing on AC circuits.
Oh.
To prove the same power divider rules that work for DC circuits works for AC circuits as well.
Okay, go to next
Okay,
one.
doctor. So do you want me to explain on this?
No,
Because, these are
I read it.
power-
I read your thesis.
Because these are the two main formulas
Mm.
for AC
Okay.
circuits.
Mhm.
Okay, next, resistance in AC circuits. Okay, this is another what I call situation we'll come across later in the waves and so on. Okay, so now when we talk about a configuration,
Mhm.
okay, that consists of only a resistor.
Mhm.
So as mentioned over here, involves only resistor. Okay, current and phase in phase with each other. That means it's moving along.
Mhm.
Moving along. Peak voltage reached same instant as peak current. Okay, but for resistor. Capacitor in AC circuit
Mhm.
involves only capacitor, stores charging as electric. That's the main function of a capacitor. So how, when it stores what you call electric, charges and stores electric, what happens to the circuit? Current leads voltage by 90 degrees. So when at time you can see the current which is in a blue form, okay, leading the current in this situation.
Mhm.
Okay, so the what you call the values A, B, C, D, and all these are explained over here.
Yeah.
So it charges, discharges, charges, discharges. and so on. Inductance in AC circuits involves only inductor. Now reaches peak after quarter cycle after voltage peaks, because okay before that source current as magnetic field as current moves. The moment there is a current, it will start to store and the current as magnetic field,
Mhm.
and eventually converts the stored magnetic field to current. The magnetic field to current when it stops. Okay, so current lags voltage by 90 degrees.
Yeah,
So
current
you can
is
see
lagging.
the current lagging
Yeah.
behind the voltage, and you can see the symbol for the inductor there.
Mhm.
Okay, so next will be this end of the part one.
Mhm. You want a break or something?
I'm just going to have the things.
Yes, go ahead, go ahead. Okay, I understand your speech. You have some remarks to consider.
Okay, okay.
So later you refer Dr. Yamuna's copy So you will know what are the things you have to do.
No, I will discuss with you later.
Oh, okay, no problem.
Should I start?
Yeah, go ahead.
Okay, the second part, data analysis. So some of the samples are shown over here. For RLC circuit, which is also a series circuit, okay, consists of R1 inductor with a value of 1 kilo ohm.
But you have done the simulation for 2 branches, correct?
Yes, sir.
Go ahead.
And you have inductor over here. Again, the value is assigned. Capacitor. Again, the value is assigned over here. Microfarad. And you can see 50 hertz over here. The power is supplied plus, minus, and volt over here. So this is a circuit, okay, that is being used for part of the data analysis. Okay, part of the data analysis for serial. Okay, the example of wave that you got. Okay, we go according to RLC over here. So R here represents resistor wave, and the B over here represents inductor, capacitor, and the voltage over here. So this is a sample of it.
Okay.
In a waveform.
Yeah, this is for good case because I don't see any problem on any wave.
Definitely.
But I've seen there are so many distortion and so many fluctuation on other waveforms. Okay, go
Some
ahead.
was gone through the amplitude modulations as well.
Go ahead.
Okay, so this is the sample circuit for the combination of RLC, resistor, inductor, and capacitor again. So you can see previously it was arranged on a serial configuration. Over here is arranged on parallel. Now definitely when you arrange it in a serial form and parallel form, definitely there will be a difference in the weight as well.
Why? There is a diode in between.
Diode is due to the very advanced oscillation from this side. Okay, power. So it neutralizes.
There is some oscillation when you connect
Yes.
in parallel because it forms tank circuit. Go ahead.
Okay, this is the sample graphs over there. Again, the arrangement is the same. Okay.
But
Resistor.
why C, the capacitor, I think. Capacitor, the waveform is inconsistent and
This is what you call a
looks unstable.
distortion. Yeah, unstable. But then again, the power wave, the voltage, same.
Go next.
Okay, this is the example for Monte Carlo analysis where the values are varied, as you see over here. So different values are assigned to the software, and then you will get the waves over here. So basically, again, resistor, inductor, capacitor. So with the different values assigned on the for the circuits.
Okay. What is Monte Carlo analysis?
Monte Carlo analysis is where you vary the value.
Value of what?
Resistor, inductor, and capacitor. Okay, within the specific range. To test whether what you call you go out of the ideal simulation, how it reacts. So what do you call the series circuit Monte Carlo analysis? Okay. Again, there is difference, distortion.
Why is it so?
this is actually representing inductor. Okay, so at times when we are in what do you call, the values differs, the stability will be achieved among the components. This under parallel circuit, again under same, the same situation you can see over here, and definitely inductor number 2, okay, and the power you can see the waves are almost in line. This is the most important. Okay, this one varies according to the value just now I mentioned. Okay, again this is another example. Okay, so it all depends on the combination of components with the values that is assigned as well as the configuration, whether they can work on the circuit with the specified current, okay, compatible. If you're not compatible, then this is what you do. Okay. So let me touch on the conclusion. Okay. So power divider rule for the DC circuit that published in 2006, as already explained and show the article as well. Okay. So it's already been proven, and at the same time, approximately true for the AC circuits. It's proven also based on the values that we saw as well as the waveforms just now. So the total supply power is equal to the sum of individual components' power regardless of input sources. Okay, so what are the inputs?
Previously it worked for DC and now it is working for AC.
AC.
Is that what you mean?
Yes. Okay. So the total supply power is equal to the sum of individual components' power in regard to the components' value, according to the value that we assign as well. Okay. And selecting proper
in
value.
regard to components value, that means what? It depends on component values.
Yeah,
Otherwise it will give distortion.
definitely. Because components are also with a different combination. But definitely, as we saw just now, the last
How many circuits you simulated, Mr. Desmond?
for AC or DC?
For AC?
For AC, actually, some of it I already put it over there, but definitely I've tried more than that in my laptop. Okay, at times you can get the correct one, so which I already published over there, and due to some values and varies, so I don't put it over there. Okay, some of it I already stopped.
So the components value is an important factor now.
Yes.
Okay, go ahead.
Okay. Selecting proper values for the component.